participant numbers starting to count up now that we've opened the stream. So welcome everyone who's arriving and coming in. Great to have you all with us. And I hope, like me, you're all primed to learn about embedding for categorical data with neural networks. I'll just give everyone a minute or so to arrive, because after I open the stream for participants, it takes a little while to sort of drain the queue into the stream so that everyone can see what's going on. Yeah, I've got William Caicedo joining us tonight from the Movio office, if I'm not mistaken, one of your meeting rooms. Hopefully that's the IP behind you on the blackboard there is nothing too sensitive.
Yeah, it's not.
Cool, cool. Alrighty, so that's great. I think we can start kicking into things. Hello, everyone. Just a little bit of housekeeping to begin with. I'd like to provide you all now with a Discord link, which you can use to join into the Discord chat room at your convenience to fire questions in. And you can type in those questions at any time that they occur to you during the whole stream, and then we'll answer them towards the end in a QA session. I'll keep an eye on them as well. If there's anything that seems like a really good thing to jump in with, I might interrupt you, William, if you don't mind. But for the most part, we'll just leave them to towards the end. We'll have a Q&A session, and I might have a go, if I can get it to work with Zoom, to let some of our participants ask questions interactively on the mic as well. If you would like to do that, if you could just click on the little Q&A icon in your Zoom and just type in mic, please. You can just type in MIC during the Q&A, and I'll see your name there with the mic, and I'll be able to unmute you. And you'll see that I've given you an unmute request, I think it is, and you'll be able to unmute yourself as well, and then you'll be able to maybe ask a more detailed question that's hard to type. And again, we'll save that for Q&A at the end. Right. So IBM is our key sponsor, so I want to thank them for continuing to make this meetup possible and providing venues when we're having physical meetups. And also I want to thank David Stokes, who's helped us out with the Zoom setup. He's the founder and principal consultant at Technology Systems, and he's the co-organizer at Product Tank Auckland Meetup. So thanks to Product Tank Auckland for leading this webinar initiative to support us and other New Zealand meetups to continue adding value to their members while we've got COVID-related interruptions going on. Finally, I just want to take a moment to say the Auckland AI Meetup believes Black Lives Matter, and I know that this all started in the States, and some of you might sort of wonder, like, why do we need to jump on the bandwagon? But listening to voices in New Zealand, it's clear that this really resonates with parts of the community here, and I think it is an important moment in history on a global level. So I just want to reiterate that any form of racism is completely against the Auckland AI Meetup's Code of Conduct, and we will, continue to step up efforts to have a diverse array of speakers. And I think one area that we can do better is that we need more diversity on our organizer team. So if you know of anyone who is in any underrepresented groups who might be keen to be a part of the organizer team, I'd love to hear from you. And there's a large variety of ways that people can get involved. It looks really good on CV or on LinkedIn. So if you like organizing, emceeing, networking, finding speakers, helping with web stuff, or you know someone who might be keen, then we'd love to hear from you. Okay, so yeah, I'd like to introduce William Caicedo. Hopefully I've pronounced that right.
Yeah, yeah, that's fine.
Please feel free to correct me.
Caicedo.
Caicedo?
Yeah.
Great. Thank you,
Awesome.
William Caicedo, who is a senior data scientist at Movio and a PhD candidate at AUT. And he's great at making complex concepts like this understandable to plebs like me. So I'm really looking forward to another one of your really great clear talks laying out this topic for us. So yeah, without further ado, William, I'll let you take over. Thanks so much for being with us tonight. And yeah, I'll put myself on mute now until I'm back to facilitate the Q&A session. But I'll be around if there's any technical difficulties. Yeah, so please go ahead, William.
Thank you very much. It's an honor to be here. Thank you for having me again. It's very nice to have the opportunity to talk about things that I find really interesting, and so yeah, so that's what we're gonna do. Have a little chat about neural networks and how you can use them to encode categorical data, which is probably not the first thing you would think about neural networks, that they are useful to do this kind of thing. But in fact, they are. So we're gonna talk a little bit about that. And I hope you guys enjoy it and find it interesting as much as I do. So this is our outline for the talk. We're gonna discuss what is categorical data, why is there a problem, where it's not really a problem, but sometimes it could be a little bit hard to deal with, and how do we solve this situation when we are trying to fit machine learning models with categorical data, and specifically how we can use neural networks. In the general case of using neural embeddings, which is something interesting, I'll be talking about that, what that means. And one particular application of this, which is recommended movies. And this is because I work in a company that does AI and machine learning to recommend or connecting people with the right movie. So we use machine learning and we go through a lot of data to try to find what people like, and then try to connect them so they can go to the cinemas and watch the things they really want to. And then some concluding remarks to kind of round up everything we talked so far. Yeah, so I work here at Movio as a data scientist. I've been here almost a year, and I have been able to learn a lot in working productionizing machine learning models, specifically deep learning models and everything. So essentially, that's why at this point in time, I'm able to talk about this. So let's go. Let's start. What is categorical data? So in short, everything that can, like any kind of data that can take one of a limited set of possible values, which are categories. For example, car brands, hair colors, all the things like that. Those are categorical data. And essentially not numerical. That's why they also call it nominal data, right? And one particular thing about categorical or nominal data is that these categories have no intrinsic order to them. There is no intrinsic ordering. So if you have, for example, 3 different hair colors, just for an example, if you have, like, I don't know, brown, black, or blonde, there is no really ordering. So it's not like first comes blonde or first comes brown or whatever. So that's not really the case. And categorical data is part of a greater data taxonomy. You have, of course, categorical data, and as we said, categories have no intrinsic order. But you also have ordinal data, which is similar to categorical data in the sense that both are like, instead of numbers, they're like words. But in the case of ordinal data, there is an intrinsic order, so that makes it a bit easier to work with. And finally, you have numerical data, which is proper numbers. And what actually differentiates numerical data from, let's say, ordinal data is that the numbers are equally spaced. They are equally spaced, like, for example, on a scale. So that makes it pretty much, it's not an easy thing to do, but it's much easier to work with that kind of data than, let's say, categorical or even ordinal data. So sometimes this is a problem when you're dealing with categorical data, and especially with certain types of categorical data. It can be a little bit of a problem. So why is that? And the reason is some of the machine learning algorithms we use are just designed to work with numbers. For example, linear regression. If you see at the screen, you'll see that that model that's there, it depends on having a theta vector that's actually numbers. So if your data are not numbers, so you might be forced to like go from whatever it is to numbers, or like convert it from whatever it is, hair colors, types of cars, brands of cars, or whatever that is. You have to find a way, you'll be forced to find a way to convert that into numbers so you can plug them into something like linear regression or logistic regression of all sorts of machine learning algorithms. There are some machine learning algorithms that are able to deal with categorical data as it is, for example, decision trees. But we also see that some of the leading decision tree-based algorithms like gradient boosting machines and specific implementations of the gradient boosted machines like XGBoost, they also tell you that you have to convert the categorical data into something that is numeric in nature. So it can be a problem, or it can be a chore that you have to solve, like something you have to do in order to plug the data properly into your machine learning algorithm of choice. As I said, for example, if we are dealing with hair colors, right? For example, black, blonde, and brown. If you go and like try to apply a very naive encoding, in this case, assigning a code 0 to black, 1 to blonde, and 2 to brown, that probably is not going to work very well most of the time. And the reason is there is no reason to believe that brown should be higher in value than blonde, or blonde higher in value than black. Actually, yeah, it doesn't make sense. So it's pretty much it's not the principal choice of encoding. It's pretty much arbitrary. And if you go down that path, you might find problems. So we probably need to come up with something that's a little more principled. So how do we do it? How do we do this? How we come up with a more principled alternative to translate from categorical data into numerical data we can plug into our machine learning algorithms? So I already like dropped this word, encoding. And encoding is exactly this, the process of converting those categorical data into numerical representations. And the simplest technique, that's actually not a naive one, but it's simple, still very simple technique, is called one-hot encoding. For example, we're still dealing with our black, blonde, brown categorical data, which is hair color. How do we convert this into numerical data? Well, if you use one-hot encoding, you will convert each possible category into a vector. And that vector is going to have n-1 binary variables inside. So if you have, of course, if you have n categories. In this case, black would be 0, 0, blonde would be 1, 0, and brown would be 0, 1. So it's like you have indicator variables that tell the algorithm that one specific characteristic of feature is present or not. So that's why it makes sense. That's why it's more principle. And it's actually statistically valid as long as the number of indicator variables is not n. Because let's say if we have 3 hair colors and we say we're going to convert that into vectors size 3, in this case, black would be 0, 0, 0, or sorry, black would be 1, 0, 0, blonde would be 0, 1, 0, and brown would be 0, 0, 1, you end up with a problem with this multicollinearity, which means that the representation you have chosen for your categorical data, that's a little bit hard for me, those columns end up being linearly dependent to each other. That can give you problems when you're trying to use algorithms like linear regression, because linear regression depends on the inversion of a matrix. And when you have a matrix in which some columns are linearly dependent, that inversion is not possible, or you can have stability problems if you use other algorithms that don't involve matrix inversion. So to avoid that, we use n-1 indicator variables. Very good. In practice, how do you do one-hot encoding? So you have a bunch of data in a database and you're trying to get that with SQL. You can do some case statements in an SQL query, and that works pretty well. You end up with as many categories as you need, binary categories that you can further process that into something that is numerically stable. Or if you use something like scikit-learn, there's the one-hot encoded class, or if you use Spark ML, which is awesome too, there's a one-hot encoded class, and you can use either of those to process your data and convert your categories into numerical columns that you can plug into your algorithm choice really easily. All right, but one-hot encoding doesn't cut every case. There are some cases in which this can be unfeasible or downright impractical. If the number of categories is too large, right? You might run into problems. For example, if you're trying to do NLP, you would say, all right, how do I represent a text? One very common way of representing text is something called bag of words. So what you do in a bag of words is that, in a bag of words approach is that if you have, let's say, 10,000 words, you would then represent each word as a 10,000 dimensional vector, right? In which you would have all zeros, but just one, which would represent specifically the position of one word. So you end up with this one-hot encoded vectors, but it's like very sparse vectors, because it's like 10,000 positions in the vector and only one is not a zero. Because of that, because the inputs are too sparse, this can be inefficient in a computational basis. But also, you could end up with very poor results if you're trying to do NLP, like predicting sentiment prediction or something like that. And that's one of the reasons researchers have tried to look for something else, a different representation, because one-hot encoding backwards has limits. It doesn't work well every time. And in general, if n is large, you might end up running into some trouble. So it's not a perfect tool, and it's not always the right choice. However, there are alternatives. And it's funny because all of this comes essentially from natural language processing. But the good thing about all of this is that its application is much more general. It's not just about natural language encoding, but you can use the same principles in different areas to solve different kinds of machine learning tasks. So about neural networks, we know that a neural network is a pretty interesting machine learning model, because what it's trying to do when it's being trained is that on the hidden layers, the neural network is trying to adapt to find a representation of the input data that's efficient. It's usually compressed, so you can discard all of those features that are not really important to solve your task, your machine learning task. So these representations that neural networks compute in the hidden layers are usually compressed, and of course there are transformations, highly nonlinear transformations of the input data. So that's what we say, that hidden layers in a neural network are feature projectors. So you take your input features, and these input features are projected into some high dimensional space or lower dimensional space. It depends on the specifics of the layer, but it's definitely a different space. And what the neural network layer does is taking your data and project it into that new space. And usually in that space, linear classification is much easier. If you carefully design the architecture of your neural network, you can end up with compression. For example, you can compress data. The autoencoders are probably the most well-known example of this. When you have an autoencoder, you actually have your input, and somehow this input is compressed into small, quote-unquote, representation. And that representation is guaranteed to somehow keep the interesting bits or the useful bits of the input. It's a little bit like as if you were performing principal component analysis, but this would be a nonlinear principal component analysis. And the architecture and the error function of the autoencoder are designed to find a compressed representation that's efficient and that can actually keep or retain the interesting bits of the input, so you can reconstruct the original input from that compressed representation. So we know that neural networks are able to do this. And we also know that if you're dealing with one hot encoded data, which is highly sparse, you can project those inputs, the sparse inputs, into dense vectors. And what do I mean with dense vectors? I mean that these are vectors with no zeros. These are vectors with actually real numbers, and then like 2.5, 7 point something. And you can end up, remember, your 10,000 dimensional vector that only had a 1 in them. You can actually compress that into a, let's say, 64 dimensional vector that has numbers in all the 64 dimensions that are not 0. These are dense vectors. So we know all of these things about neural networks at this moment. So how is this useful for our task? Well, to answer this, we have to first remember something that happened in 2013. This was like a watershed moment. Now we all talk about transformers and big neural network models and everything, but sometimes we forget that the one technique that actually really like changed NLP as far as neural networks are concerned is word-to-vec. Because Mikolov and his team in 2013, they found that you're under the right conditions, you can transform words into vector representations, and the semantical, somehow the semantical relationships between words were retained in this vector representation. And then You could do all sorts of funny stuff like word algebra, for example, things like king, I don't know, like king minus man plus woman equal queen, things like that. And there are some web pages that are really, really funny because they do all sorts of experiments doing this word algebra with what they call word embeddings, created with this technique called word2vec. Because as I said, this way of encoding the words keep the interesting semantical regularities. And this is the reason why this particular technique is so much better than just using bag of words. So in a nutshell, here in this slide, you can see what word2vec is about. There is something called the distributional hypothesis in linguistics, which means that it's something, I mean, I'm not a linguist, so probably I'm just butchering everything. But what I take from the distributional hypothesis is that the meaning of words is actually related to the way the words appear on sentences. So if you have two words that have the same distribution, I mean, they appear in the same places with similar context in all the words, it's probably safe to assume that these two words have similar meanings. For example, we have here, the kid is my child and the boy is my child. You can assume that since the context in which these words appear usually is the same or very similar, then you can assume that the meaning of kid and boy, it's probably similar too. So this is the distributional hypothesis. So how does word2vec work? You have a one hot encoded input, which is a 1 times n vector. This is a sparse vector that represents one word. Let's say it's the word kid. So you have a 1 here that indicates that kid is the word and everything is a 0. And then you feed this into an embedding layer. This is actually a neural network that has 2 layers, one hidden layer and a final layer. So you feed this bag of words into an embedding layer that's actually n times m. That's the dimensions of the layer. You have then after this a softmax layer that's m times n, and you end up with a vector of predicted word probabilities. But what are we trying to predict exactly here? So this variant of word2vec is called skipgram. And the skipgram variant of word2vec actually works this way. Let's say you have a corpus. A corpus is just a text, a lot of words in a text. And then you choose, let's suppose this is just one sentence in the text. And every position here corresponds to a word. So we have defined that we're going to take 5 words, and then the word in the middle, we're going to call it a skip word. And then the words in the left and on the right are called the skip window. So what we're trying to do here is we're trying to use the skip word in the center to predict the words that occur in the skip window. So in essence, we're trying to predict the context of a word given that particular word. So you can see that using that structure, we end up with this data set here in which you're trying to use W3, word 3, to predict word 1, and then to predict word 2, and then to predict word 4, and so on and so on and so on. So if you have kid and boy and these 2 words appear in the same context or similar context, you end up with similar pairs here in your data set. So when you train the model to predict context given a word and you have similar context, what's going to happen here is that this weights in the embedding layer are going to take a structure that's going to reflect the fact that words that have similar contexts have to have vector representations that are close to each other. For example, you can say that these vectors have a small cosine distance. The angle between them is actually small, which means those vectors are very similar. And they are similar because these vectors, which represent words, these words occur in similar contexts. So this was a watershed moment. The original Word2Vec paper probably a little bit hard to follow, but there are many resources on the internet where they take apart all the complexity in it. So most of you might be already familiar with this, but those of you who are not, I just encourage you to go, because it's really awesome, and it's really, using Word2Vec, you can get really good results using NLP without having a big transformer or a big neural network. Actually, I've done, in part of my PhD, I've done some NLP, and you can get pretty decent results just using a simple Word2Vec transformation to deal with words and sentences and text in general. All right, so you use a corpus to get this word embeddings using a Word2Vec technique. You find that similar words tend to cluster together. And this is just because similar words are words that occur in similar contexts. And this technique is able to detect that. And if you have a way of encoding those words that actually respects the semantical information, it keeps it, those embeddings or those encodings you get as a result are going to be much more useful than the back of word representation, which is, remember, this is a one-hot encoded representation. And the problem in this case with a one-hot encoded representation is that this representation doesn't really capture the semantical information that's present into sentences. All right, so that's how Word2Vec works. And then if you're following so far, we have taken categorical data, high-dimensional categorical data in the form of text, and we have encoded it into numbers, specifically into vectors. And these vectors can have the dimensionality you like. In our past example, that dimensionality was M. So you can define M to be 10, 12. There's actually some rules of thumb to find that M, given N, which is the original dimensionality of your bag of words representation. But that can be generalized to all sorts of categorical data. And not only that, it can be generalized to all sorts of entities that have some sort of hierarchy. For example, you have a car, and let's say your car has different types of engine, different types of tires, different colors, or all of these characteristics. You can possibly find a way using neural networks to encode all of these characteristics into just one vector that's going to be like your car vector, but it's going to take into account all of those pieces that actually are part of the car. We can generalize this Word2Vec thing into something that's much more powerful. And this is because these representations learned in the hidden layers can actually capture these useful regularities of categorical data. Let's say you have two cars, and let's say those cars have the same, this is a stupid example, but it works. You have two cars, and these cars have the same brand of tires. So that's actually a characteristic they have in common. And if you use neural networks the right way, you could actually take those multi-column data, which is the car with brand and type of tires and color and everything else, and encode this data in a way that cars with the same brand of tires actually are closer together in this vector representation you're going to get than cars that don't have the same type of tires. The big catch here is that you need an adequate objective. In the Word2Vec case, the objective was trying to predict the words that appear in the context of one specific word. So if you can come up with a task like that makes sense for your particular problem, you can then take your categorical data or your tabular data in the most general sense and encode that into a vector that actually respect this semantical regularities of the original data. So we've seen, we can extend these principles to cover many, many situations. And the result is that you're gonna end up with dense vectors that can be whatever dimensions, whatever many dimensions you want them to be, you want them to have. And these vectors are going to capture whatever it was on the original data that was categorical, or that was a set of different categorical columns. And you can use these vectors, we use them in downstream tasks. For example, when you do NLP, you get your word vectors using something like word2vec, and then you use those word embeddings to do something like sentiment analysis. Or you use those word embeddings in any other NLP task that you want to use them for. So talking a little bit about what I do here at Movio. I've been involved in some projects. One of these is pretty experimental. We use machine learning algorithms to predict what moviegoers want to watch, right? And we use this, we try to do this given the moviegoer history. So what you watch in the past really is going to allow us to predict what things you would like to watch in the future, what kind of movies, what genre of movies, what actors you like in movies, and so on and so on and so on. So in the company, we have transactional data, which is people watching movies in different exhibitors or cinemas around the world. And we also have movie metadata. For example, we have casts, genre information, censor rating information of the movies, and we also have access to moviegoer demographics as well. So with this data, the task is predicting what the moviegoers would like to watch, given their attendance history, which means the movies they have watched in the past. So in this experimental project, a deep neural network was designed to predict the probability of attendance. And from the very beginning, the architecture of the network was designed to coax the network to end up computing movie embeddings. So I'm gonna go back here. So remember, we have for each movie, we have cast, genre, and censor rating. We have many other things, but just let's focus on those three things. The cast, which is the actors that work in the movie, the genre, it could be like horror, action, sci-fi, and the censor rating, which is PG, R, all of those things. If you think about it, the things I have mentioned, all of them are categorical data, not numerical data. And in the case of cast, that's actually very high dimensional, because a cast can be represented as a vector, let's say a vector size 4 of actors, but each actor is a name, and then how many actors are there. So if you're trying to use something like one-hot encoding to represent all possible actors, you end up with a really huge matrix. So this is all categorical data. So what neural networks are able to do with this kind of data? So I'm going to show you a peek of the architecture of a model we have been working on. So we have this attendance prediction network, whose architecture is not really important at the moment. But what's important is the data we actually feed into this attendance prediction network. So you have a movie, and each movie is the collection of its genre, its cast, its censor rating. And then you put this in, right? And not only the new movie, you're trying to predict how likely is for a moviegoer to watch, but you also have, for this particular moviegoer, their movie history, the movie they watched before, and the one before that, and the one before that, and then you have a window that's size N, with all the movies this person has watched into the past. So remember, using that history, we're trying to predict the probability for this moviegoer to watch this new movie. And for each movie, you have the genre, the cast, and their censor rating. So in this section, we have something I call a movie projector, which takes that information and gives back, as a result, a dense vector that captures the interesting regularities of the movie. So if you have a vector for a movie that's, for example, let's say Avengers. It's a sci-fi movie, but it's also an action movie. And you have a cast, which is Robert Downey Jr., and this one, and the other one, and the actor that does Thor and Captain Marvel. So you would expect that that vector is similar to other vector in which the movie was also sci-fi. And let's say Robert Downey Jr. was in that movie too. You would expect that those vectors are closer together than Avengers compared to some of the movie that's like a thriller or is a comedy, for example. It turns out that if you train this network and you constrain the network to reuse the weights on each step of the movie history, you end up with vectors that capture these semantic regularities. So inside this sub-network, you have something that takes care of the movie genre and the rating, something that takes care of the cast. Actually, the cast itself has to be translated into a dense vector on its own. And then when you get everything together, you translate everything again into just one dense vector. And the good thing about all of this is that you just have to connect layers. You don't have to really think, oh my God, how am I going to like handcraft this transformation? You just connect everything together, and using gradient descent and backpropagation, you end up, or the network ends up learning the good stuff about what's closer to what and what's similar to what. I have a couple of examples here, actually 4 examples, using the TensorFlow projector. These are all movies. For example, here we have a movie called Penguins of Madagascar. And then in this transform space induced by the hidden layers of this network, this deep neural network, we see that according to the network, the most similar movies to Penguins of Madagascar are Ice Age Collision Course, Kung Fu Panda 3, The Lego Movie, Trolls, and The Scrooge, Moana, and so on and so on and so on. And what do these movies have in common? They all are kids' movies, so it makes sense. And we haven't told the network directly that that's the way it's supposed to be. But training the network on a sufficiently large data set, these vectors appear without us doing too much, actually. In the case of Avengers Endgame, according to our movie embeddings, we have that Avengers Infinity War is the closest movie to it. We have Doctor Strange, Justice League, Thor, Ragnarok, Ant-Man and the Wasp, and including things like Solo, a Star Wars story, which is also cool. This is all sci-fi movies, superhero movies, most of them into the Marvel cinematic universe, but also the odd DC movie. But it kind of makes sense that these movies are close to each other. And finally, just not to spend too much on this, in this case, Mission Impossible Fallout. According to this embeddings in this transform space, Solo as a Star Wars story, it's the closest one to it. And then The Mummy, and it's interesting because The Mummy, this is The Mummy, not the old one, this is the new one. It's actually not very good, the one with Tom Cruise. So Tom Cruise is in both movies. So that's probably why those movies are so close together. John Wick Chapter 2, what you can see the similarities. Dunkirk, which is guns and explosions too. Aquaman, like, you know, the superhero. So you can see that even you can see that actually there are regularities that the network is picking up. And it's not us humans telling the network, this is close to this. It's just because of gradient descent and because neural networks are actually cool, that this is actually happening. I think I could probably show you a couple more examples because the guys from TensorFlow they have done an awesome job, and they have, yeah, I'm gonna show you this. This is really cool. They have open source an embedding projector, so you can use your own embeddings, whatever you have, and use this embedding projector. Oh, sorry, let me check this. Yeah, for some reason I cannot share this. Anyways, I'll go back to my presentation. Let me see. Ooh, something's happening. All right, anyways. The good guys of the TensorFlow project.
So sorry, William, your screen isn't shared at all right now.
Yeah, for some reason I cannot go back to sharing. I'm trying to select the, here what I want to share, and it's not working at the moment. Let me try again. Cool. Yes, finally, I did it. It was actually my mistake. Can you see it now?
Yes, we can see your whole screen now, including that website.
Awesome. All right. So what I was saying is that the good guys in TensorFlow, for the TensorFlow developers, have taken something called an embedding projector, and that was a part of the TensorBoard plugin for TensorFlow, and they have open sourced it. And then you can go to the projector.tensorflow.org website. You can upload whatever embeddings you have, and then this nice website uses JavaScript to run some dimensionality reduction algorithms, like for example UMAP, which is my new favorite, or TSNE or PCA or whatever you want. So what I did was that I trained my neural network, and I extracted the weights of the hidden layer that I showed you before, and I just wanted to see what happened. And then I found interesting stuff. Here you have Guardians of the Galaxy 2. And it turns out that the most similar movies to this are Black Panther, Thor Ragnarok, Avengers Infinity War, Spider-Man Homecoming. Down the line, Guardians of the Galaxy Volume 1 must be. But it's interesting that it has detected, or it has somehow recognized that all of these movies are part of the MCU universe, the Marvel Cinematic Universe. If we do something like John Wick, let's say John Wick Chapter 2, so I'm going to show you here. It comes back with interesting suggestions. The most similar movie to it is John Wick Chapter 3, something called Mile 22, which I don't know what it is. The Mummy, The Great Wall, American Assassin, Mission Impossible, Fallout, Baby Driver. So all of these things make sense. If I was to use these vectors for some other application, I actually know that these vectors are able to capture interesting regularities in movie space. So if I reuse them for something else, I know that it's like I'm not training my model from scratch, because I'm doing transfer learning in this case. I'm doing it for movies. You can do it for whatever tabular data you have. If you have tabular data in which a lot of the columns are categorical data, and they are like somehow linked because they are part of an entity or a concept, if you come up with the right task, you can use a neural network, you can train it, and you can find, you can actually find a way of getting dense embeddings that are going to be usable for any other machine learning tasks you think of. All right, I'm gonna go back to my slides now. That's awesome. So finally, concluding remarks. High dimensional categorical data can be efficiently encoded using neural networks. There's an asterisk there because it's a catch. You gotta come up with a suitable objective. And don't despair if this, I mean, if you're trying to get your embeddings and you come up with your objective and you train a neural network to predict whatever you want because you're trying to get embeddings out of it, the results, the performance of that network doesn't have to be great. It doesn't matter if it's not really great. If you're trying to, for example, in my case, if I'm trying to predict who's gonna go watch what, I don't have to really solve that task with high performance. It doesn't matter. Just the fact that I'm training the network to do that, it's gonna force the weights to find those embeddings. So even if the original network sucks, you can reuse those embeddings in another task, and you can actually perform pretty well in that downstream task. Well, those hidden layers act as feature projectors. The dimensionality of that projection space can be set to suit the task at hand. You can use 10-dimensional vectors, 128-dimensional vectors. It all depends in that task, the ultimate task you're trying to solve. As I said before, there are some rules of thumb you can use, like, for example, the square root of the original space. That's probably a good choice for your for the dimension of your embeddings, right? And whatever embeddings you create, you can use them in downstream tasks. These three things pretty much apply for every task at hand, or every possibility or context. All right, that was it. Thank you very much for your time, and I hope that you have found that as interesting as I find it. And I think that if you have any questions now, I'll be really happy to hear about them.
Hey, thanks so much, William. I learned a lot and had a lot clarified personally from that. That was great. You know, I never realized with the one hot encoding how important it was to go n-1 to get a proper statistical representation. That never really clicked for me. And the way I conceptualized that, it was always just, you know, have one column per category, but clearly, you know, you need to do that n-1, otherwise it's kind of an off by one error, right? And the wrong dimensionality. So yeah, anybody here, I hope you enjoyed the presentation as much as I did, and feel free to jump in anytime with questions. You can use the Q&A, the Zoom webinar chat, or the Discord. I've got all of them open. I'll see your question. And so there's no questions yet. It must have you know, been really clear. But perhaps just while we're waiting, giving anyone a chance, we could just have just a small chat about some of these concepts. And yeah, because there are certainly some things that I'm still trying to wrap my head around. So it seems like it's really important to find, it's all about finding relationships between kind of multiple categorical features, right? So am I correct in saying that this isn't a technique you can use to take like just one feature, like one categorical kind of column, I suppose, and just turn it into something numerical for your neural network? Or can you do that?
Well, I guess you could, but I mean, you gotta be careful, because it could be like trying to kill a mosquito with a bazooka. You know what I mean? If you have, let's say you have one categorical column with only 3 possible categories, using a neural network for that could be a little bit overkill. One hot encoding is gonna solve the problem just fine.
So what if I had one category with 10,000 options?
I think that, I mean, personally, I would try a neural network because, so
So thinking of the movie example, right? We have
the actors, the actor column can have like 2,000 different values, right?
But doesn't the neural network sort of learn certain actors corresponding with like certain genres, or corresponding with certain, I don't know, directors or whatever else it is that it was finding relationships with. But what if you only have like that one category? Can it
Okay.
still work to turn it into a numerical, like a vectorized form somehow?
Okay. So if you have, if your cast column is just one actor, you probably didn't have enough data to figure out the relationships, because if you, what you always have is just
Oh, sorry,
um,
to clarify, I'm meaning you only have the actor column. So you have lots of actors, but you have no other categorical stuff. Like,
okay, yeah, exactly. Let's suppose that's the case. You only have a column that's called actors, right? If you only have one actor per row, um, this probably wouldn't work. And the reason is that there is no way to figure, or probably, yeah, I'd probably still like try it, but it's hard to see in my mind that it will work unless you have some way of relating actors together. If you can find actors that tend to work together, right, in movies, then you would think that this procedure would give you vectors. Let's say you have two actors that work a lot together, then their embeddings should be closer together than the
mhm,
embeddings of actors that never work together. You know what
mhm.
I mean?
Yeah,
So
so
it
it's
wouldn't
really
work.
sort of
Yeah,
converting the problem into one where you effectively have multiple categorical features. It's hard for me too. Like sort of like actor one, actor two, actor three, something like that, and
exactly,
like you can start to find the correlations. Okay, so
exactly.
it's really about say you have some problem space where you have five features with continuous numbers or ordinal numbers, and then you have five features which are purely categorical. Um, then your sort of your first pass is taking um, just the categorical features and then turning each sample into a vector representation,
Yes.
which represents those categorical features, and then um, perhaps recombining that vectorized form of each sample into um, the continuous features,
Yeah, it's like
and feeding them into a network.
it's like as you said, in this case you would take just your categorical columns and take them apart, do your neural network magic, and then you end up with vectors, and then
Mhm.
all of those categories end up with a compressed vector that actually has all the information you need from them, and then you put that back into your data set and you ignore your original categorical columns and you just use those vectors and you put them back, and then you train whatever algorithm on the whole of the data set. Yeah, something like that.
Yeah, so would you want one neuron per dimensionality of those vectors, plus one neuron for each continuous feature, and then that would be the size of that layer that you'd
Of the
feed that
input
into?
layer, yes, of the input layer, yes.
Uh-huh. Right. Okay.
Yeah, but then again, for this to be actually useful, you need to have either a lot of columns, or, well, it's always a lot of columns, but what I'm trying to say is that a lot of categorical features, or categorical features with a high dimensionality, because then it's when you're going to actually find that this is useful for you. You know what I mean? Otherwise,
Right.
you're perfectly well doing one-hot encoding, and even doing some more exotic things like label encoding or target encoding that are used in different algorithms. For example, the people from CatBoost, they came up with this target encoding mechanism or algorithm.
Oh, please tell us a little
That,
bit about that if you have time.
sorry.
Please tell us a little bit about that if you have time.
I used it once actually, because I was trying to acquaint myself with CatBoost, so I read a little bit about it. It uses the this target encoding thing uses the information of the targets of the things you're trying to predict, and some statistics of that column, they use them to encode those categorical features. For example, if you're trying to predict, I don't know, the age. This is a really stupid example, but you're trying to predict the age from the skin, from the hair color of someone, right? So you would take all the people with black hair like me, and then you would like compute the mean of the age of these people, and then that value would be the number you would use to encode the black hair color. But that works, it seems to work, but also it has some, I mean, there are some shady stuff because you're actually using part of the answer and like leaking it back into the training set. But then the CatBoost people came up with a way to avoid that particular problem, and it actually works really good. So it's another thing you could possibly use. So if you don't know about it, you can just like read a little bit. There's a lot about it on the internet about label encoding and target encoding.
Right. Maybe you could check a couple of keywords into the Discord for us that will help us find that, or perhaps a link to the article that you're talking about would be
awesome.
Be amazing. Yeah, I guess other things that jump to mind are things like ordinal encoding. Sometimes you might be able to find some kind of natural order, even though it's categorical data, right? Like maybe it's like level of academic achievement. So you've just got something like junior high, high school, college, university, PhD, or something like that. They're just categorical data, but
exactly.
You may still be able to get something sensible out of it by just having some numerical values.
Yeah, I guess sometimes we're a little bit fast to quick to discard many things. When if we think a little bit more about it, we can actually do some nice feature engineering. For example, if we're talking about the days of the week, the first thing it would come to mind, how do I encode that? I would say, okay, let's use some indicator variables like one-hot encoding. But then you could also think that, okay, Monday and actually Sunday and Monday are close together. So maybe it's something cyclical. So instead of using one-hot encoding, I can use like a sine function or a cosine function to encode the fact that the days of the week repeat. You know what I mean? So if you think about it, you can actually come up with interesting stuff, right?
So it's basically domain-specific encoding at that point.
So this is it's funny because I dream with an algorithm that doesn't need like domain information, right? Something you just can throw to anything and it would do perfect. But unless you have a lot of data, or unless you have a very strong inductive bias, I mean, your algorithm has a strong inductive bias that actually reflects what's happening on your domain, you probably need to get into the domain, become some like an expert of the domain, so you can do adequate feature engineering in every specific case.
Yeah, sure. Like I've heard of a domain-specific example where somebody was trying to do some predictive analytics on demographics, and one categorical thing they had was the domain of the email address, and that wasn't something that they could use directly with their neural network, but they found that there was a correlation between the domain of the email address and their salary brackets, which was a continuous number that they could then plug in, and it was relevant, so yeah, sometimes it's just a matter of getting a bit creative with the domain-specific stuff, right?
Yeah, exactly. That's
cool.
True.
So yeah, there's no open questions. So yeah, thank you very much to everyone who's joined us tonight, and yeah, continues to be with us. Thank you for taking your evening to join us, and thank you so much, William, again for bringing your giant brain and laying some of the stuff out for us. It's much appreciated.
Thank you.
And we look forward to hopefully having you with us again sometime in the future.
Thank you very much.
Great. Thank you, everyone, and good night.